Hello, I'm Andrey Klimentyev and I'm a solutions engineer at Flant.
Hi, I'm Dmitry Stolyarov. I'm CTO and co-founder of Flant.
Yeah, we both work at Flant.
We don't want to waste your time telling you about what our company does, but of course we will appreciate it if you check our site.
And we don't want to waste your time because today we are going to talk about...
Yes, we are going to talk about...
cloud-native shell scripting.
So let's talk.
Yeah, let's do it. Before expanding on this notion of cloud-native shell scripting, we'd like to talk about Kubernetes. Yes, this platform that we all know and love, from its wonderful API to well-thought-out programming patterns upon which the Kubernetes is built. Instead of working with low-level system stuff, such as configuration files, systemd units, or even containers, we operate on a higher level of abstraction. Such high-level concepts as deployment, stateful set, secret, or even node are available to Kubernetes users.
When I think about Kubernetes API, I imagine the file server having folders for each kind of the object, and objects or resources being YAML files on that server. And it has simple HTTP API which allows us to do three things with this server. First, we can get a resource, knowing its kind and its name. Second, we can change the resource. And what's important is that we can only store the object if it's valid. So if we try to put the object into the wrong directory, or if it's just malformed object, the operation will be denied. Third, we can watch resources. To do that, we ask the server, and we immediately receive the same result as if we would use the get method. But if the resource changes, we instantly receive a new version, and if it changes again, we receive the update again, and so on. So basically, Kubernetes, in some way, is a YAML file server with three methods. Of course, there are many others, but we skip them. We just need those three. But the server, except for storing information, does completely nothing. And to put life into the Kubernetes, we need controllers. The second most important fundamental thing in Kubernetes, in my list. Generally, we have two types of controllers. Controllers of the first type read from Kubernetes, process information using some logic, and write back to the Kubernetes. And controllers of the second type, they also read from the Kubernetes, but they change in some way the state of external world. Let's just quickly look into what happens when a user creates a deployment in Kubernetes. The deployment controller, it's part of kubectl manager, gets this information and creates the replica set. Then the replica set controller gets the information and it creates two replicas, two pods. But these pods are not scheduled, so the scheduler gets them, schedules them, and writes their YAMLs back, but updated, having node filled in them. And then we have kubelets running on different nodes. And they get their pods and update information in external world, but this time it's Docker. And then, what happens then? Then, basically, almost all the chain repeats, but in reverse order. So, kubelet checks status of containers, calculates status of the pod, and reports it back. Then, replica set controller receives it, updates status of the replica set, the deployment controller does the same, and then user, if he watches, receive final status, or he can get it later if he doesn't watch. So Kubernetes is all about controllers acting together, and if you are going to automate anything, you need to write controllers.
But we all are sysadmins, aren't we? And we all love Unix philosophy, and we all are used to piping and shell scripting. So when we want to count files in a directory, what do we all do? Well, of course, we use find and WC. And when we want to find the process by name, we use ps and grep, and maybe an extra grep. But when we want to find top 10 IP addresses in the log, we cat the log, extract the second field, because we know that it has an IP address, then sort, count unique values, sort again, and take the first 10. And that is our result. That's how we used to do things. And on one side, Kubernetes adapted to it very well. If we want to find most used images in our cluster, we can use kubectl and tell it to get all pods from all namespaces and extract the image field from them. And then use the same approach as with logs. Sort, count, unique, sort again, and take the first 10. But what should we do if we want to act on a change?
Controllers. As I've told you, and I think as we all knew, Kubernetes is all about controllers. And to be successful in the Kubernetes world, we need to be able to write controllers. So what we are trying to do is to implement a tool that will allow us to write controllers, or you can call it operators, simply and effectively, but by using those methods we are used to as sysadmins. And we think we quite succeeded in that. Let's look at an example.
We've got a Kubernetes cluster with a default namespace and a secret in it. We've also got a lot of other namespaces, and some of them are marked with a special label. What we'd like to do is take our source secret and copy it into these namespaces. Some namespaces get added to the cluster later, and some of them might have a special label. If it has, we'd like to take our source secret and copy it into them as well. If a label is removed from a namespace, we'd like to remove the secret from it. If a source secret changes, we'd like to propagate these changes into labeled namespaces. If a secret is removed from a namespace by accident, we'd like to immediately restore it. But before we take a look at the implementation of such a controller in Shelloperator, let's take a look at what Shelloperator is. Shelloperator, like all other workloads in the Kubernetes, is deployed in a pod. In this pod, we've got hooks directory, into which we place executables, written in Bash, in Python, in Ruby, you name it. We name these executables hooks. Shelloperator subscribes to Kubernetes events and objects, and if something of interest to us changes, a Shelloperator executes these hooks. Now, how does it decide what hook and when to execute? To solve this problem, a hook has two phases. When Shelloperator starts, it executes each hook with a config argument. Each hook outputs a YAML with its configuration. Once the configuration phase passes, each hook gets executed when a relevant to it event happens. It is executed without any arguments, and it gets passed a binding context, a special JSON. About that we'll talk a bit later. Now, if you use Bash, we highly recommend that you use Shelllib, which simplifies writing hooks in Bash. You'd want to implement two functions, one for configuration phase, in which you output your binding configuration, and one for the normal execution, which contains your logic. Now, we've discussed what a hook is and how it subscribes to Kubernetes events. But what objects are we interested in? We are interested in a source object, source secret, since we'd like to know when it changes and whether it exists or not. We are interested in all our namespaces in the cluster to check whether they are labeled or not. And we are interested in destination secrets to check whether they are synced with the source secret. Let's start off with configuring a subscription to the source secret. Binding configuration for it is extremely simple. We define that we are interested in secrets in a default namespace with the name mySecret. Once configured in such way, a hook will get executed if a source secret changes, and it will receive a binding context which has a name that we've configured and a full object. Next up, the namespaces. We specify a kind namespace and also include a new field that's named JQFilter. Now, what is a JQFilter? Let's get to the console and find out. If we kubectl get namespace and output it in JSON format and pass it through a simple JQFilter, we'll get a new JSON object that contains two fields that we are interested in. Once configured in such way, a hook will receive a binding context that contains an array of filter results for each namespace that we in a cluster. These filter results will contain a namespace's name and a Boolean value, which describes whether it has a label or not. In previous example, we received a full source object, a full Kubernetes object, but since we aren't interested in it, we can remove it with a keep full objects in memory false statement in a binding configuration, and it will be missing in binding context. Last but not least, destination objects, destination secrets. We subscribe to all secrets with the managed secret yes annotation label and pass it through a JQ filter, which contains its secrets namespace and a resource version that we pass into a annotation when we create a destination secret. We use resource versions and store it in the annotation of a destination secret to compare secrets. Yes, we can compare secrets byte by byte, but why do so when Kubernetes already stores resource versions for us? If configured in such way, a hook will execute when some of these objects change. If any of these objects change, it will receive three binding contexts that we've described previously. It will be like a small snapshot of a cluster. Using this information, we can devise a simple algorithm. We iterate over all namespaces and we check whether it has a label or not. If it has a label, we compare source resources version to destination's resource version. And if they are similar, if they are the same, then we have nothing to do. And if they differ, then we execute kubectl replace or create. If a namespace does not have a label, then we have to make sure that no secret is present in the namespace. So we check if a destination secret, if a destination object exists, we kubectl delete it. And if it does not, well, then we do nothing. A bash implementation is simple as well. We iterate over namespaces, we check whether it has a label or not, and if it does, we synchronize secrets. And if it does, we synchronize secrets, and if it does not, we delete secret. The delete secret function contains 3 lines of bash. We check whether a namespace has a secret, and we delete it by a static name mySecret. When we synchronize secrets, we compare the source secrets resource version to destination secrets source resource version that we've placed in an annotation. And if they differ, we construct a new object and we execute kubectl create or replace to make sure that the destination secret is a carbon copy of a source one. As you can see, we've skipped some parts of a script. You can see the full version on the URL below. And that's how we've implemented a simple controller in 35 lines of YAML, 20 lines in bash, and a Shelloperator that binds them all together.
Secret copying is not the only thing you can do with the Shelloperator. Few more examples. Let's imagine deployment having 3 pods. And this deployment, pods of this deployment, use config map for some configuration. They might use environment variables, or they might mount config map as a file, but that's not important. What is important is that when these pods were starting, config map was in some state. Let's call it version 1. So all our pods are running with this version. But if config map changes to another version, pods will continue running with the old version. And what we usually do in such cases? Yes, usually we add something to our pods template. Let's add the annotation with config map checksum. So now our deployment had this checksum in it, and all the pods also have it. So when we change the config map, we should not forget to also update the annotation. Or we can use the Shelloperator and program a hook that will subscribe to the config map and change the checksum. So When a user modifies the config map, Shelloperator notices the change and updates checksum, and then the Kubernetes automagic happens. Kubernetes removes one of the pods, creates new one, waits while it becomes ready, and then repeat the same with 2 other pods. So our deployment becomes fully in sync, fully running with the updated config map. We are not going to delve into the code for such a hook, but you can find the whole examples by following the link below. It should be like here, or it probably will be bigger, so like here. Okay, another example. And let's jump back to the beginning, to the slide with YAML file server. We should remember that Kubernetes allows us not only use the object kinds that are embedded, but it allows us to create our own kinds. So we can create the kind with the name MySQL database. Why not? And this kind will have only metadata, only name and namespace. So basically we have our Kubernetes with our namespaces, and we can create MySQL databases in them, and we can use Shelloperator to watch for resources of kind MySQL database, connect to the real MySQL database, and synchronize the list of databases between what we have in Kubernetes, between the desired state and what we have in the MySQL server, the observed state, between desired and observed state. Okay, example number 3 or 4. We want to monitor the cluster network. And one of the easiest ways to monitor the network, we know it from our previous sysadmin life, is by using ping. And to do that, we of course use Shelloperator and we subscribe to nodes. And we only need the node name and its IP address, so we can go through the list of nodes and just ping each of them. But I want to add a few things to this binding configuration. First, I don't want the hook to be executed on any event, so I path the empty array. So when nodes are added, changed, deleted, or whatever, the hook will not be executed. But then, when it will be executed? Every minute. It will be executed every minute, and every minute hook will receive the list of all nodes, because we have subscribed to them. Okay? That looks cool, I suppose. But how do we report problems? How do we report packet loss? Let's look a bit into the code and find out. So we walk through nodes, extract node's name and node IP address, ping the node, and then we write Prometheus metric. Shelloperator allows hooks to export metrics to Prometheus, and all you need to do is to write to the file stored in pass to the file is stored in environment variable metrics path. And you should write the metric name, what to do with it. In this case we increment a counter and add the labels you need. That's basically it. So I don't know how many lines of code, but not many, and you get simple network monitoring. Okay, I suppose now your imagination is running and you have in your mind at least a few things you want to automate with Shelloperator, or maybe even a dozen. And probably that's time for us to finish, but I want to explain one last thing, but extremely important thing. Without knowing it, you will not feel comfortable with the Shelloperator. Kubernetes, Shelloperator, event happens. Shelloperator executes a hook and it's running. But then another event happens. Will Shelloperator start another instance of the same hook? But what if 5 events happen simultaneously? Will Shelloperator run all of them in parallel? And what will happen to our resources, to our memory, CPU? How can we manage them? No, Shelloperator will not do like that. Shelloperator has queuing mechanism, so all events are put into the queue before being processed. Let's imagine we have two hooks, and having two hooks, our queue will have events for two hooks. The first event is for one hook, so it's executed and the event is passed to the hook, and when it's done, the queue proceeds. Three next events are for another hook, and they are popped out of queue and passed to the hook as a batch, so hook receives the array of events, the array of binding contacts, or these events can be even combined into a bigger one, and we have been actually using this all the time through all the examples. The group field is responsible for grouping. Moreover, you can have as many queues as you want, and you can have as many hooks as you want. And you can use one queue from two hooks, or you can use two queues in one hook, or create any combination you want. And all you need to do is to add just one field into the binding configuration. If the queue name is not specified, hook is just run in the default queue. And this queuing mechanism totally solves all the resource management problems.
A Shelloperator has an older brother that is named addon operator. If you recall, a Shelloperator subscribes to Kubernetes events, executes hooks if something interesting happens. These hooks can change something in the Kubernetes cluster or affect something in an external world. If we replace Shelloperator with addon operator, we can bundle a Helm chart with it. Then the hooks that previously affected the Kubernetes or the external world can set, modify, or delete values in a value store of an addon operator. If such a change is detected, an addon operator executes Helm and passes it a Helm chart and the value store. The rendered chart is applied to the Kubernetes cluster. If Shelloperator is a collection of hooks that are triggered by events, an addon operator is the same thing plus Helm integration.
Okay, that's it for today. Thank you for your time. We hope you enjoyed it.
We'll be happy to answer your questions right now, and we will be answering in the Slack channel for the next few hours.
And yes, just one thing. How can you try Shelloperator? The easiest way is to open the Shelloperator's GitHub page, and you'll find the Getting Started guide there.
And if you liked it, don't forget to star.
And subscribe to our YouTube channel, we just have started it, and check out our other projects. I think you might find them useful. See you!
See ya!